Hi, this is Quantum Mechanics by Unify Physics. Today we discuss the wave function. Okay. So what exactly do we mean by the wave function? We have discussed it in some detail in our previous classes. Today we'll just make it more explicit and we'll see how we can go from one representation to another representation. Okay. We are dealing with two representations in this session. We'll talk about the coordinate and momentum representations. Okay. We'll do a couple of problems. Right. Now, what do we mean by the wave function? So, from our previous classes, we are clear that in quantum mechanics, the states are represented by vectors in Hilbert space. Okay. States are represented by vectors in Hilbert space. Okay. The state of space, the space of states, the space of states in quantum mechanics is known as the Hilbert space. Okay. This means that every possible state is represented by a vector in the corresponding Hilbert space, etc. Okay. Now, there's another important property that we use in quantum mechanics. Observables are represented by operators. Okay, not any operator, but Hermitian operators. And Hermitian operators have a nice property. They are eigenvectors from a complete set, or we can construct a basis out of the eigenstates of a basis. You can always construct a basis out of the eigenstates, okay, or the eigenvectors of a Hermitian operator, all right. So the basis of your Hilbert space, you can either choose the eigenvectors of momentum operator, the eigenvector of position operators, or the eigenvector of the Hamiltonian operator, anything, okay. And these are different representations of the same vector, all right. Now, suppose we use the coordinate representation. That means that we are using the position operator or the eigenvectors of the position operator as the basis set. Right. So you might be familiar. We said that if you have a basis set phi I, then the ket psi or the state vector can be always written as a linear combination of this. Okay, we have seen these things. Okay, this we call as the basis set, and generally in quantum mechanics we are always choosing basis vectors which are eigenvectors of any Hermitian operator. Okay, this is convenient. All right. Now, when you go to the coordinate representation, unlike this, we have a discrete here we have a discrete set of eigenvectors. In the case of position operator, we have got a continuous set of eigenvectors, which means that each point in space is a possible position eigenvalue, for example. All right. So, correspondingly, this is a continuous set of eigenvectors. In this case, we have a continuous set. All right. So, instead of this expansion coefficient here, for each point in space, you have got one expansion coefficient. All right. For each point in space, you have got one expansion coefficient, or corresponding to each point in space, you have got a complex number. All right. That's what we write by psi of x here. It's just a generalization of this Ci into the continuous basis. Okay, and these are the position vectors. Right. Now, this thing, okay, once we set the basis, the expansion coefficient alone. If we are talking in a discrete basis, then you can write a column matrix C1, C2 up to Cn. All right. And once you fix the basis, you don't have to talk about the basis. You can use these expansion coefficients, for example, in a column matrix, and consider this as the state vector. Okay. This is known as a representation of the state vector. Similarly, we can use psi of x as a representation of the state vector psi. Okay. You can use psi of x as a representation of the state vector psi. This is known as the coordinate representation. All right. Now, what happens if you choose the momentum eigenvectors as the basis vectors? All right. Then we get another set of expansion coefficients. All right. Sometimes we write it as psi tilde of p, or sometimes we'll slopily write it as psi of p. Okay. So, but you have to remember that by psi of p, we mean these are expansion coefficients in the momentum representation, all right, or you can call this as the wave function in the momentum representation. So, here we have got an expansion coefficient, or we have got a complex number corresponding to each possible value of momentum, all right. So, this is known, this psi of x here, the expansion coefficients, the collection of expansion coefficients when you use eigenvectors of the position operator. Okay, this is known as you can call it as the coordinate space wave function, and in this case, this is known as the momentum space wave function. Okay, the momentum space wave function. Okay, or we can call this psi of p as the momentum representation. Okay, the state vector in the momentum representation. All right. Okay, that's that. Now, in coordinate representation, okay, we don't go into the details. The position operator is the position itself. All right. For example, if you have got this position eigenstate x, right, and you ask what's the possible value of position, it's x. Am I right? So the position operator is the position itself, but the momentum operator is minus IH cross d by dx. It's a what do you say, differential operator. Okay, it's a differential operator. Differential operator. All right. Now you know that in quantum mechanics, this momentum, the position operator and momentum operator, what do you say, satisfy this important commutation relation. All right. In one way, you can say that this is the defining, this is the definition of momentum and position operator. So in the momentum representation, if x is the, what do you say, if x is the position operator, then you can convince yourself that in order that this commutator is satisfied, the momentum operator has to be minus IH cross d by dx. So if x is the position operator, then the momentum operator has to be minus IH cross d by dx if this commutational relation has to be satisfied. In fact, that's one way to derive this particular momentum operator, by starting with the commutation relation. Okay, or you could start directly with this momentum operator and actually check whether the commutation relation is satisfied, or we can see that the commutation relation is actually satisfied. All right. In the momentum representation, again, you got a momentum eigenstate. You ask the question, what's the momentum? All right. You ask the question, what's the momentum corresponding to this? It's p. All right. So p of momentum operator is just the momentum itself. All right. So we have got px cap equal to px, and x cap here is IH cross d by dpx. All right. Remember that here you have got a minus sign, all right, which means that the momentum operator in the coordinate representation is minus IH cross d by dx, whereas the position operator in the momentum representation is IH cross d by dpx. All right. So you see that when you go from x to px, okay, so here, so if when you go from x to px, I has to be changed to minus I. All right. You can again see that only then the commutation relations will be satisfied. Okay. So when you go from x to px, it involves a change I to minus I. Right. So you can trace it back to the fundamental commutation relations. Okay. All right. Now time evolution, we will be coming back to this. All right. This is known as the Schrodinger equation. The time evolution is determined by the Hamiltonian operator. Okay. Now we are, instead of the general state vector, which is an abstract vector in the Hilbert space, we use the coordinate representation. All right. So we are looking at the expansion coefficients and ask how they evolve with time. Okay. Generally, there is also a time dependence here. Okay. So the question is, how does this evolve with respect to time? Okay. And that's defined by the Schrodinger equation. All right. And how do you generally find the wave function? In order to find the wave function, you have to construct the Schrodinger equation and solve it. Okay. It's just like in Newtonian mechanics. In order to find the state of the system, okay, state of the system, you need to construct Newton's equation and solve it, okay, to find the position and momentum as functions of time. Here also, in order to find the wave function, the state of the system, you have to construct the Schrodinger equation in the given physical situation. Okay. For example, there might be a potential, and then you have to solve it. That's a way to do that. We'll be doing problems using Schrodinger equation later on. Okay, so this is an overview of the position and momentum basis. All right. You have got the position operator, it's a vector operator, so to speak. All right. And you'll get the position. This, because if it's in three-dimensional space, in order to locate a point, okay, in order to specify the position, you need three coordinates. That's why I write r vector here. R vector means x, y, z. Okay, you need three numbers. Similarly for momentum. All right. What do you mean by psi of r vector? It's you can say that it's the projection of the psi. Okay, this psi of r vector and psi, these are different things. All right. What is psi? Psi is some abstract vector. So don't confuse between these two. Generally, you don't lose much by confusing, but it's better to have it clear in your mind. All right. So this is an abstract vector in the Hilbert space. Okay. What is this thing? These are the coefficients of this vector in the basis set formed by the eigenvectors of the position operator. I hope that's clear. Okay, you take the eigenvectors of the position operator as the basis vectors and ask the following question: what are the expansion coefficients if this is the basis? All right, or this can be called as the projection of psi along the position eigenvector r vector, or along the basis r vector. It's just like saying like this, okay? In three-dimensional vector space, you have got xi plus yj plus zk, for example, okay? So you can write this vector as a column vector xyz. But the logic is same, right? Now, how do you get this expansion coefficients? You say that x equal to the scalar product of I with r vector. Am I right? You can say this is the projection of r vector along I. And in the three-dimensional vector space case, real vector space, we write this as I dot r vector. Alright, so because of orthonormality, I dot j will be 0, I dot k will be 0, and I dot I will be x. Okay. In the same way, psi of r vector is written as the projection of psi along the eigenvector r vector. Okay, this is known as projection or scalar product. Okay, I hope that is clear. Or you are actually projecting out the expansion coefficients. All right, you are getting the expansion coefficients here. Similarly here. All right. So this is the question. What is psi of p vector? Generally, sometimes you write a tilde there. Tilde. Okay. What's psi tilde of p vector? These are the expansion coefficients. When you expand this psi, in the momentum in the basis set formed by the eigenvectors of the momentum operator. Okay, these are the expansion coefficients. And how do you get that? You project the state vector onto each of the bases, and you get the corresponding expansion coefficient. All right. So since for each value of momentum you have got a complex number, we write it as a function. Okay, we write it as a continuous function. All right. Now, by the property of scalar product, we know that if psi of r is the scalar product or the projection of psi along r vector, then psi star is just this. All right. We know this property. AB is equal to BA star. Okay. That's part of the definition of a scalar product in Hilbert space. Okay. Similarly here. And we have got a completeness relation. I think we have talked about this before. Okay. So the completeness relation means that if you choose a basis, it has to be complete, which means that if you take any arbitrary vector, you should be able to expand it in terms of this basis vectors. And if you should be able to expand any arbitrary vector in terms of the basis vectors r vector, then it can be shown that this condition is actually satisfied, or this condition has to be satisfied. I think I have explained this in one of the previous sessions. All right. So it's one, they say, but actually it's the identity operator. Okay. It could be generally it's a matrix. All right. So it's we better write I cap here or 1. Okay. But by 1 we mean that it's generally the identity operator. Okay. All right. All right. So r vector cap. Okay. And its p vector is p vector cap, or the momentum operator in the position coordinate basis is minus IH cross del r. Okay. So if you are talking about 3 dimensions, if it is 1 dimension, we can say px cap equal to minus IH cross d by dx. When there are 3 dimensions, it is px, py and pz. So generally you can write as del vector r. Okay. Similarly here we can write del vector p. Okay. We are just generalizing what we wrote before. All right. So in this case, r vector, the position operator is the position vector itself. Right. The position operator is the position vector itself, and the commutation relation means that the momentum operator has to be a differential operator of this form. Okay. All right, and x with px equal to IH cross, x with px equal to IH cross. All right, so whatever representation you choose, the commutator relations are actually invariant. All right, so the operators, these are operators, you have to be careful. Sometimes we forget this hat here, but you have to be careful. Okay, these are operators. All right, so the commutation relations are actually invariant. Whichever representation you use, the operators are defined. You can say that the operators are defined by these commutation relations. All right. Okay. Now, how do we connect the momentum and position spaces? All right. We can start by looking at the momentum eigenvector on the coordinate basis. Okay. Is that clear? So we say that P is the momentum eigenvector. All right. But this P, this momentum eigenvector, is again a vector in Hilbert space. So you can expand it. All right. You can expand it in terms of any basis, for example, the position basis. Okay, you can expand it in terms of the position basis. you should be able to expand this in terms of the position basis, okay, coordinate basis, because basis is not unique. You can choose any basis you want, okay. Now you ask, what's this psi of x? All right, this psi of x will say that it's a representation of the momentum eigenvector in the coordinate representation. It's the representation of momentum eigenvector in coordinate space, okay, or coordinate representation. I hope that's clear, all right. And it can easily be shown that it is 1 by square root of 2 pi h cross e raised to ipx by h cross, all right. It's called a plane wave, okay. So what is this? This is the representation of momentum eigenvector in coordinate space, okay. In other words, we can say that if we are working only in coordinate basis, we can say this is just the momentum eigenfunction. This is just the momentum eigenfunction, okay. Momentum eigenfunctions are definite momentum states, and you can actually check this. How do you check this? You start with the operator minus h cross d by dx. This is the momentum operator, all right, and you act it on this term. You will see that you get a constant multiplied by the same wave function, all right. So you can convince yourself that this is actually a momentum eigenfunction. How do you use that? How do you do that? You take the momentum operator in the coordinate basis, which is minus ih cross d by dx, okay. Now you act it on this state, on this wave function, all right. You act on this wave function, and you will see that you get p, or some a number multiplied by a real number multiplied by the same wave function, okay, which means that this is an eigenfunction of the momentum operator, okay. So that's an exercise for you. Show that e raised to ipx by h cross, okay, divided by square root of 2 pi h cross, if you like. This is known as the normalization factor, okay. All right, so ipx by h cross is a momentum eigenfunction. Of course, it's a momentum eigenfunction, but I want you to convince yourself, okay, just to be clear that everything is consistent. How do you do this? What do you mean by momentum eigenfunction? Momentum eigenfunction means that, okay, so momentum eigenfunction means that if the momentum operator acts on that function, you get a constant multiplied by the same function. So generally operators change one function to another, okay. If you are talking about a differential, if you are talking about the coordinate basis, all right, operators are differential operators, okay. So differential operator usually changes a function into another function, obviously, okay. But there are certain classes of functions which do not change, all right. They just get multiplied by a number when a differential operator acts on it, all right. So such functions are called as the eigenfunctions of that particular operator. In this case, you can see that this is actually an eigenfunction of the momentum operator, okay. Similarly, so if this is proven, if we find this thing, okay, this xp bracket xp, you can call it, okay, then px is just the complex conjugate of this, and we have it here, all right. In 3 dimensions, this 1 by square root of 2 pi h cross, it becomes 2 pi h cross raised to 3 by 2, okay, for obvious reasons, because there are 3 dimensions, all right. Oh, and here, I'm sorry, we have got a p vector dot x vector, okay, p vector dot x vector divided by h cross, all right, okay. So I should correct that, all right. That's in 3 dimensions. Okay. Now, how do we fix this this normalization constants? How do we fix this normalization constants? All right. So if you are familiar with these things, these wave functions are known as non-normalizable wave functions. You cannot normalize it to 1 in the usual way. All right. Okay. We won't go into the details. These are non-normalizable wave functions. Non-normalizable wave functions. Why? What do you mean by a normalizable wave function? It means that if you take psi of x modulus of psi of x square dx over all space, okay, let's say minus infinity to infinity, you should get 1, all right. But if you do modulus of psi of x here, what do you get? It's just constant. So if you integrate a constant all over space, you get infinite. So that means that this wave function is non-normalizable, all right. But these wave functions are really important also. All right, even though you may not find a physical state in this particular wave function, these are very important in physics. Right? So Dirac found a different way to normalize these things. Okay, this is known as Dirac normalization. Okay, Dirac normalization says that you have to demand, okay, p vector with p vector prime as delta of p vector minus p vector prime. This is known as the Dirac delta function. Dirac delta function. Okay, so demanding this thing, you can fix this normalization constant 1 by square root of 2 pi h cross. Right, this is important. This is known as Dirac normalization. So it's not exactly normalized to 1, and you cannot really interpret it as some sort of a probability density, but we can still use this. We can demand that if you take different different momentum eigenvectors, okay, you should, and you take the scalar product with itself or scalar product between different eigenvectors, it should be it should give you the Dirac delta function. Okay, demanding this, you can show that the normalization constant in this case, okay, we call it also normalization constant, is 1 by square root of 2 pi h cross. Okay, but you have to be very clear that the probability interpretation does not really work for non-normalizable wave functions. All right, but these are important. We still have to work with them, so we use something analogous to normalization, and we call it as Dirac normalization. All right, okay. Now the next question is, I said that the representation is not unique. All right, you can choose one basis or the other. You can choose the eigenvectors of the momentum operator, take that as the basis, it's all fine. You can take the eigenvectors of the position operator or the Hamiltonian operator, anything you like. Okay, you can take this as the what do you say, the yeah, you can take any basis you want, but then the question is, how do we go from one representation to another? All right, so what if you have got a momentum representation wave function, how do you go to a position representation? Or if you have the position representation, how do you go to the momentum representation? Okay, so it's easy to show that thing. The answer is a Fourier transform. Okay, the simple answer is a Fourier transform. Okay, so if you want to go from one representation to another, use the Fourier transform. If you need to go from the position basis to the momentum basis, they are connected by a Fourier transform. Okay, we can show that here. As we said, psi of p we can write as the bracket p psi. Okay, we have explained this. All right. Now, in quantum mechanics, usually when we are stuck, or usually in physics when we are stuck, we either multiply by 1 or add 0. These are the things that we do, and sometimes it helps. All right. So here what we do is that you multiply by an identity operator. Okay, there's nothing wrong in putting an identity operator in between here. Okay. All right. Now we can expand this identity operator in this form. It's integral dx x with x. Okay, this is known as the completeness relation. Completeness relation. All right, so you put this in here. Okay, all right, so what do you get? You get something like this, dx x psi. All right, because this p we can pull it out of the integration is over dx, you can write it like this. And what is this x with psi? It's simply psi of x. It's simply psi of x. All right, and since this, it doesn't matter whether you put it outside or inside the integral, so you have got this bracket px and bracket x psi. All right, okay, I hope that's clear. Right, it's nothing, you just put it in here. Okay, so p, and then you have integral dx x x psi. Okay, that's what we have done. Right, now we can pull it, take it inside, so this becomes dx px x psi. Now these are numbers, these are complex numbers. This complex number has a name, it's known as psi of x. Am I right? This is the representation of psi in the position basis. And what is this projection x onto p? We know that it's e raised to minus ipx by h. We have got here. We have got this thing. Okay, we use this bracket px is 1 by square root of 2 pi h cross e raised to minus ipx by h cross. So you just substitute it there, and you get this result. Okay, so psi of p and psi of x are connected by this thing. This is a Fourier transform. All right, you can see also then similarly, you can, by the same argument, you can show that psi of x can be obtained from psi of p by what do you call it? If this is a Fourier transform, you can call this as an inverse Fourier transform if you like, but anyway, it's also a Fourier transform. All right, by this particular Fourier transform. And you see that there is this h cross appearing here. Okay, in the Fourier transform that you are familiar with, there is no h cross here. All right, so the h cross appears here because we are going from x to the representation p by h cross. Okay, we are trying to go from x to p by h cross. All right, so if you put p by h cross as k, okay, then you get back the exact Fourier transform relation. So psi of k is equal to 1 by square root of 2 pi minus infinity to infinity psi of x e raised to minus ikx dx. All right. So these are exactly the Fourier transformations. All right. It's not very difficult to remember. You have to remember this. Okay. There may be problems. They may give you a coordinate representation wave function, ask you to find the corresponding momentum representation, or they may give you psi of x and ask you to find a psi of p. Then this is what you have to do. Okay. All right. Now we are ready to go into problems. Let's do a couple of simple problems. All right. If psi of x equal to 1 by square root of 2l for modulus x less than l. Okay. So what does this mean, modulus x less than l? All right. So this means that the limits are minus L to L. Okay. The range of the wave function, we are talking about the range minus L to L. Okay. Then modulus x will be less than L. Am I right? All right. So find psi of p. You can write psi of p is equal to, use the Fourier transform, just as we said before. Okay. All right. So since we are going from there's a small, we have to put a bracket here. All right. So psi of p is equal to, since we are going from x to p, you write 1 by square root of 2 pi h cos minus infinity to infinity psi of x e raised to minus ikx dx. Okay. Just as we said. What's this k? This is actually p by h cos. Okay. This is actually p by h cos. All right. So that is, you just substitute this psi of x that's given here, that's minus infinity to infinity 1 by square root of 2l e raised to minus ikx dx. Right? But you don't have to integrate from minus infinity to infinity because the range is given here. It's minus L to L. Okay. Okay. So let's assume that it's 0 everywhere else. Right. So it becomes minus L to L e raised to minus ikx dx. All right. So you just pull this outside and combine it here. It's 1 by square root of 4 pi h cross L minus L to L e raised to minus ikx dx. Now this is a simple integration. All right. You know how to integrate this. It's e raised to minus ikx divided by minus ik. Right. Because you are integrating over x. Now you apply the limits minus L to L. Okay. So you combine all these factors. There's a minus here and minus 1 by ik 4 pi h cross L. It's all there, and you get e raised to minus ikl minus e raised to ikl. Now you can take 2i inside. Okay, for obvious reasons, you know that e raised to ikl minus e raised to minus ikl minus e raised to minus ikl. All right, so this is there's a minus here, so there's a minus. I missed a minus there. All right, you take this minus inside here. So what's this? This is simply sine kl. Okay, or sine p by h cross L. All right, it's sine kl. Okay, that's what we have. It's sine kl divided by k square root of pi L h cross. Now you just rearrange it and simplify it a little bit because we need to write everything in terms of the momentum p, if that's what is asked. All right, so you just substitute k is equal to p by h cross, simplify, and this is the final answer we get. All right, so psi of p we obtain from psi of x by a Fourier transform, and it is sine pl by h cross divided by p square root of pi l square root of h cross. Okay, it's not very difficult. All right, so I hope it's clear. Okay, since we are using psi of p here, if you wanted psi of k, then you didn't have to put an h cross here. Right, if you wanted to find psi of k, you didn't have to put an h cross there. Right, so since we are finding psi of p, you must have an h cross here. Then it's a Fourier transform, and this it's a matter of integration. Right, the only thing is that you do this integration, okay, and apply the limits. It's not a difficult integration. It just shows that you can go from the position space wave function to the momentum space wave function by a Fourier transform. All right. So here we have got a similar problem. If psi of x equal to 1 by square root of L e raised to minus ikx, again the limits are modulus of x is less than L. That means the limits are minus L to plus L. Okay. So you just do this. Okay, just do the Fourier transform here, the corresponding Fourier transform. You know the relation. You can check the relation to go from psi of x to psi of p. Okay, since we have got a p here, you should have an h cross there, etc. Now it's a matter of integration. There's nothing particularly complicated about this integration, because when you multiply this, you get e raised to minus 2ik. So it's exactly the same integration that we did before. All right, so you can do that. You can try that. Okay, so we don't have to go into the details. The only thing I want to emphasize is that when you go from psi of x to psi of p, okay, psi of x to psi of p, there is a Fourier transform. All right, it's just a Fourier transform. So if you are careful, you can get correct answers very easily. So such questions can be asked. All right, you can try that. That's the final answer. You can check if this is exactly the correct answer. Okay. Let's do another problem. Find the momentum space representation for the wave function psi of x is equal to a e raised to minus x square divided by a square. Alright, so this kind of wave functions with an x square in the argument of exponential is known as a Gaussian. Alright, it's known as a Gaussian. This problem is of particular importance in physics. We'll see it over and over again, these Gaussian wave functions appearing everywhere. Alright, so the important answer is that, so if this is asked, okay, if such questions are asked, maybe you may not have to do this, all right? Because when you make a Fourier transformation of a Gaussian function, you will again get a Gaussian function, right? So suppose they give you an answer, they give you a question, psi of x is some Gaussian function, all right? And there are options, okay? Now you know that when you make a Fourier transform, you should again get back a Gaussian. We'll show that here, all right? That's an interesting result. So if in the options there are Gaussians, there are also Gaussians, you have to choose that. Okay, that's what we actually do here. So we have got this. So we need to find psi of p is 1 by square root of 2 pi h cross minus infinity to infinity. This is the wave function. This is the term that gives you the Fourier transform, and then you integrate it. Simple. All right. Now integrals. Okay, such integrals are known as Gaussian integrals. Gaussian integrals, and Gaussian integrals appear everywhere in physics. So there are certain techniques that we develop to do these kinds of Gaussian integrals. You might have already done it in your mathematical physics course. All right. So we can have this general result. It pays to remember this particular result. Integration minus infinity to infinity dx e raised to minus ax square plus bx equal to square root of pi by a e raised to b square divided by 4a. All right. It's a good thing to remember this. All right. So the nice thing about this result is that this is very general. All right. You might have proven it for real numbers a and b, but this works also for complex numbers. All right. This works also for complex numbers. I hope you have seen it in complex analysis. But the thing, if you want to convince yourself, you can try this for real numbers. You can try this for real numbers. How do you do that? You complete the square first. All right. E raised to minus x square plus bx. You can write it as, you have to complete the square, and there will be an extra term. Right? Now once you complete the square, you can write it as a gamma function, if you are familiar with that sort of thing, and that using that gamma function you can get back this result. All right? Or you can make some wise substitutions and maybe do 1 or 2 integrations to get this result. All right? So if you have such integrals, and if you don't know the formula, the right thing to do is you complete the square. What do you mean by completing the square? What do we mean by completing the square? All right, because this is minus ax square plus bx. Okay. All right. So you can maybe write it as minus. Okay. You can pull this minus outside, and you can write, okay, if you want, you can pull this minus a outside or minus outside. Okay. Let's pull minus a outside, and then it's x square minus b by a x. All right. So you know that this looks like a minus b whole square. This looks like a minus b whole square. Let's say, because we have an a here, this looks like c minus d whole square. C minus d whole square. What c minus d whole square? It's c square plus d square minus 2cd. So you can write 2cd as b by a x and c as x. All right, and then you can find d. Okay. So you can write this thing as something whole square plus an extra term or minus an extra term. Right, depending on how you do that. That's known as completing the square. So once you have a complete square here, you can use the properties of gamma function to do that integral. All right. So this is not a complete explanation of how to do this. I'm just hoping that you have already done these kinds of things. Okay. But for our purposes, it's sufficient to know that there exists such a relationship, which is also working for complex. All right. The only condition is that a and b can be complex numbers, but the real part of a has to be positive. Okay, if that condition is satisfied, then this relation works. Okay. All right. So what we have here? So this integration is exactly this. We have got this 1 by square root of 2 pi h cross outside and a outside. All right. So this is there, and the rest of it is exactly this, except that instead of a here, you have got 1 by a square, and instead of b, you have got minus ik. All right. Instead of b, you have got minus ik. So you just substitute it here, and you'll get the result. Right. So it's square root of pi by a. Square root of pi by a. So instead of a, you have got 1 by a square. So it's pi by 1 by a square. Alright. So that a square will go up and you will get a square root of pi. Okay. And then you have got e raised to b square by 4a. What's b square by 4a here? B square by 4a in this case is simply, instead of b, you have got minus ik. So it's minus ik square divided by 4a. Instead of a, you have got 1 by a square. Okay. Just substitute that. This is minus k square because I square is minus 1. So this is minus k square a square divided by 4. So you have got e raised to minus k square a square divided by 4 and the rest of the factors. Okay. All right. Now, if you are not familiar with this, I ask you to prove this. Okay. I ask you to prove this relation as a homework. All right. Okay. You can play around with these integrals a little bit. So the keyword, as I said, is complete the square. Write it as a square, complete square, plus or minus an extra term. Right, and extra term, you will see that it comes out nicely out of the integral, and then you can use the gamma function to do the rest, or some substitution to do the rest of it. Okay. Now here is another problem that I want you to do by yourself. The question is psi of x equal to 2 divided by a raised to 3 by 2 x e raised to minus x by, oh sorry, I forgot to mention one thing. You see that when you go from one Gaussian, all right, if it's the Gaussian, okay, the Fourier transform is also a Gaussian, all right. So you see that it's e raised to minus k square a square by 4. It's also Gaussian, okay. So the Fourier transformation of a Gaussian function is also Gaussian function. This is important, all right. We'll see more about these things, but this information, this piece of information is important. If the question is asked to find the Fourier transform, which among the following is the Fourier transform of the a e raised to minus x square by a square, or of some Gaussian function, then you look at the options and see if there are any Gaussians. If there is only one Gaussian in the options, then that has to be your answer. Okay, so such tricks can be used. Right. So we are here we have got for x greater than 0, this is the wave function, and for x less than 0, we have got 0, which means that you need to integrate only from 0 to infinity. In fact, you have to integrate from minus infinity to plus infinity, but the contribution from minus infinity to 0 is 0 by this. Okay, it says it's 0 for x less than 0. So you just do this. Now this integration is not difficult. You can complete the problem. Okay. That's enough for today. We'll continue in the next session. Thank you.